Assalamu alaikum. Good afternoon, ladies and gentlemen, and welcome to ADGM Academy. My name is Roda Dhahri, and I am pleased to welcome you all to the second episode of the Abu Dhabi Machine Learning Meetup event. In this event, we will explore the topic of machine learning at a detailed level, aiming to continuously grow the community's knowledge of machine learning, its application across several domains, with a focus on the financial sector. Today, we will feature 3 machine learning experts who will be sharing their insights based on real-world scenarios in the financial sector. Given that we will have physical and virtual attendees, please allow me to echo on some of the housekeeping rules to avoid any unexpected disruptions throughout the event. As you can see on the slide behind me, we have included the research email in the first slide, which is research@adgm.com, for virtual attendees to be able to include their questions to our speakers, and we will ensure that all questions raised by virtual attendees will be shared with our speakers for today, and we will address all the questions and comments raised through the research@adgm.com email. For the physical attendees, a handheld microphone will be rotating in the room to receive all the questions, and we will be taking all the questions after each session of our speakers. Please raise your hand if you have any questions or any points to add to our speakers. After the session ends at 5 p.m., there will be a networking opportunities for physical attendees to meet in the lounge areas outside this auditorium. Before we start the event, to shed more light on the machine learning, I would like to take this opportunity to introduce Gauthier Marty to shed more light and give a brief background about machine learning. Gauthier Marty is the founder of the Abu Dhabi Machine Learning Meetups. Gauthier, over to you, please.
Thank you, Rauda. So first, I would like to thank you to come here today during your day to listen to 3 amazing talks. So just to give you a bit of background, so I've been in the region for the past 2 years, and I've started these efforts. Slowly but surely, the community is growing because I recognize some faces, some are new, and that's totally great. The whole purpose of this meetup, it's not very formal seminar where you listen to a Nobel Prize and then you just acknowledge everything he did. It's more like trying to find people that are still building new things. So they are not necessarily like yet acknowledged, but it's more like cutting edge or new ideas, and it's totally fine at the end of the talks to debate the ideas and discuss. So that's one part. We are doing that. It's also to uncover the talent of tomorrow. So that's something we can also have, of course, and we have some today renowned experts in their field, but we are open to all kinds of talks, from industry to academia to even hobbyists that are developing some machine learning tools. So it's also a bridge also between communities, because thanks to that we can meet with people usually don't meet, and that's something that I appreciate. So I became closer, for example, with Khalifa University students, and Abdullah after will also give his vision for this community and the kind of talks we can have. But also it gives perspective. So some talks today will be very technical, but that's fine. Worst case, you don't understand anything, but you know that, okay, in Abu Dhabi, there is some guy that is an expert on that. And if you want to build a business or to hire an expert, there is this guy to hire, talk to, or brainstorm about. Or you understand a bit, and then you can open new ideas. You have an expert in your company that's maybe not well aware, so you give a pointer. Or it's actually your same field, and then during or after the talk, you can have a debate of ideas with the person. So that's really essentially the idea of these meetups. It's a non-formal forums to discuss ideas and discover what people are doing in Abu Dhabi and the UAE. So that being said, that's pretty much it. I hope that this kind of meetup will continue for long, and I want to again thanks a lot ADGM Academy for hosting us, because it's better if we can meet in person than just online on Zoom or Teams. So thanks to them again. Thank you, and yes, thanks them.
Okay.
And I will hand the mic to Abdullah, who is a colleague and also a student at Khalifa University, that can present also where the group can head on.
Thank you so much, Gauthier, and I would like to thank again ADGM Academy for hosting ADML and giving us the opportunity to see you today. So my name is Abdullah Al-Ketbi. I am a current master's student at Khalifa University. I'm studying computational data science. So through ADML meetups, we are giving these students, the opportunity to present their thesis conclusions and what they find on their thesis, and also to get a feedback for a multidisciplinary audience that can help with their studies going forward. As an example, I'm currently doing my thesis for my master program, and when I'm done, I'll get the chance to present it to the group here at ADML meetups. So I would like to encourage all the students, master students, and also PhD students to get and take these opportunities at ADML meetups to present their thesis and to get a feedback from the audience. And as my colleague Gauthier have mentioned, these meetups are usually you're not required to have a very basic and solid background and foundation to be able to present. It's open for everyone. And with that, I would like to thank you again.
And just on this note, Abdullah, I would also like to welcome some of the students who are also interested on the point that you just mentioned here with us in this event today. So on this note, I would like to welcome the students, and it's now time to meet our speakers for today's event. So for today's event, we have Oleksiy Kondratyev, who is a Quantitative Research and Development Lead at Abu Dhabi Investment Authority. Our second speaker is Matteo Manzi, a lead quant researcher at CrunchDAO, and Professor George Zubeli, who's the mathematics department chair at Khalifa University. Ladies and gentlemen, please join me in welcoming our first speaker for today, Mr. Oleksiy Kondratyev.
Hello, everyone, and thank you very much to all the organizers, ADGM Academy, Gauthier, and everyone else who participated in organizing this excellent machine learning meetup in Abu Dhabi. As you see, my name is Oleksiy Kondratyev. I work at ADIA, and today I will be talking about quantum machine learning. I'll try to stand maybe here so you can see the screens. This way. So my talk is approximately based on a new book that was released last year. This is our book on quantum machine learning with applications in finance. And as you can see from the title of this book, we have to answer three important questions. So why quantum computing? Why quantum machine learning? And why finance? So what's the motivation to even talk about quantum machine learning in finance? Well, let's start with the first question. Quantum computing is extremely powerful. In comparison with a classical way to perform computation, quantum computation is exponentially more powerful given the same amount of computational resources. There are two reasons why quantum computing is so powerful. And they derived from the principles of quantum mechanics on which quantum computing is based. So essentially, we can think about quantum computing as a different way to perform computation using the laws of quantum mechanics. In principle, we can run quantum computing on classical hardware. The only problem is that we would run into memory issues very quickly. But again, in principle, quantum computing is just different rules to perform computation. And the laws of quantum mechanics make these computations extremely efficient. Specifically, two features called superposition and entanglement help us to process objects differently and in a far more efficient way using quantum computing rules. The second question is why machine learning? Why applications of quantum computing to machine learning? And here the answer is the following. Everyone probably knows about sort of the flagship use case for quantum computing, which is factoring integer numbers and breaking RSA encryption. But we are very far from actually doing this because existing quantum hardware, existing quantum computers are not perfect. They're small scale, they're noisy, very fragile. So it's unrealistic to try and use them for the most famous quantum algorithms like Shor's algorithm or Grover's algorithm. But there is an area of research where quantum computing can actually be used productively right now, even with existing what we call NISQ, noisy intermediate scale quantum hardware. We can productively apply quantum computing to machine learning tasks, to building generative models, to building discriminative models, because there is a family of quantum computing algorithms that don't suffer from noise as much as search algorithms, for example. So here, during this presentation, we'll look at several QML algorithms that can be productively used on existing quantum hardware. And finally, why financial applications? And here, the reason is the following. Very often in other fields, in physics, in chemistry, in biology, in medicine, we work with stationary distributions. So when we have a data set, samples in these data sets are IID. But this is not the case in finance. So finance is all about working with time series, all about working with non-stationary probability distributions, with data sets where samples are not IID. And this leads to the whole range of very complex problems. So probably finance is the area that generates most complex, most hard to solve problems computationally. And therefore, it's a very rich area for research. So it's very tempting to take use cases from finance and see how we can productively apply the rules of quantum computing on existing quantum hardware and see what happens. Okay. Before we talk about quantum computing, let's spend 1 minute talking about classical computing. So what is a computation? A computation can be defined as the transformation of one memory state into another memory state. Or in other words, we can think about computation as a function that transforms information. And in classical digital computing, the most fundamental memory unit is binary digit or a bit of information. Traditionally, we denote two possible values as 0 and 1. Functions that transform a memory state in classical computing are called logic gates. These are functions that operate on binary variables, so Boolean functions such as logical AND, logical OR, exclusive OR, not AND, and so on. With these functions, with these logic gates, we can construct addition operators, multiplication operators, and then everything else. So that's how classical computing works. So mathematics is very clear. But in order to perform computation, we always need some kind of physical substrate on which computation is performed. Even though computation itself is substrate independent, in order to perform computation, we need some physical system. And there are many possible physical systems that can be used for classical computing. Electrical switches that can be on, off, or open, closed. It can be voltages, like 0 volt or positive voltage, and so on. If we think about classical computing, various kind of systems that implement the rules of classical computing, and then we would try and apply different rules, the rules of quantum mechanics, to the same kind of system, what would happen? Well, the first thing that we notice is that if we have a system that can exist in two states, then the rules of quantum mechanics will tell us that such system can exist in superposition of states. So in quantum computing, we again would have states 0 and 1, which are well-defined states, something that we can get after measurement. So if we have a quantum mechanical system, a quantum binary digit, a qubit, and we measure it, we get just one bit of information. We would get either 0 or 1, two possible states. But until measurement, before this quantum mechanical system gets in contact with the environment, the system can exist in superposition of the states. And we can write it down as state psi, which is a superposition of states 0 and 1 with some coefficients, alpha and beta. These coefficients are probability amplitudes. These are complex numbers, and they are not probabilities. So when we measure a quantum mechanical system, a qubit, we can get either 0 or 1 with some probabilities. If a system is in superposition of states 0 and 1 with probability amplitudes alpha and beta, then absolute value of alpha squared will give us the probability to get 0. And absolute value of beta squared will give us the probability of getting 1 after measurement. But before measurement, it's a superposition with some complex probability amplitudes. The fact that these probability amplitudes are complex numbers is very important because effectively the whole principle of quantum computing is about manipulating on probability amplitudes that can interfere, and sometimes they would interfere constructively. They would increase after applying quantum logic gates, or they would decrease, so they can interfere destructively. And this is effectively how we perform computation. The quantum circuit, the quantum algorithm is all about manipulating probability amplitudes such that the probability of measuring the right desired outcome is the highest. Now, if a quantum state can be described with the help of two probability amplitudes, two complex numbers, it means that mathematically we can think about a state of a qubit as a unit vector in a two-dimensional complex vector space. So in this space, we would have two standard basis vectors, 1, 0 and 0, 1. And these basis vectors we would interpret as our state 0 and state 1. And then state of a qubit would be a superposition of these two basis states. So that's what we see here. However, in this form, we don't have a real intuition about a state of a qubit. We have just two complex numbers, and we don't know actually what we're talking about, what kind of object we are dealing with. So it's much better to transform these coefficients and effectively move from two variables, alpha and beta, to other variables, theta and phi, which we can interpret as rotation angles. So if we perform this transformation and we move from alpha and beta to theta and phi, in this case, we can visualize a state of a qubit of our tiny quantum mechanical system as a point on a unit sphere. This unit sphere is called Bloch sphere, named after Swiss-American physicist Felix Bloch, with angles theta and phi describing how sort of our qubit moves on the sphere. If we put theta and phi equal to 0, we can verify very easily that we get state 0, so vector 1, 0. And if we put theta equal to pi, again, we can easily verify that the state would correspond to state 1, this basis vector 0, 1. And then we also have all possible other combinations of these two variables, and we can effectively cover the whole Bloch sphere by manipulating on vectors theta and phi. So when we talk about a qubit state, we can visualize it as a point on the unit sphere. Position of the qubit on the sphere is determined by two angles, theta and phi. And a quantum logic gate, a function that changes this, the qubit state, can be seen as a rotation. So we talk about rotations as quantum logic gates. So if a qubit is a unit vector in a two-dimensional complex vector state, then what is a rotation? A rotation is a 2x2 unitary matrix. So any 2x2 unitary matrix can be seen as a rotation matrix and as a quantum logic gate, one qubit quantum logic gate. Here we have two examples. One is a very simple matrix called Pauli X, which implements the X gate. And if we perform very simple linear algebra operations, we can verify that the X gate would transform state 0 into state 1 and state 1 into state 0. So this matrix, Pauli X, implements the logical knot. Then we have the Z gate, which is Pauli Z. Again, by simply performing some algebraic operations, we can see that it will leave state 0 unchanged, and it would transform state 1 into state -1. So after measurement, we will get exactly the same outcome, but this phase is very important, right? Because remember, quantum computing is all about manipulating on probability amplitudes. So change in probability amplitude will help in quantum computing circuit. And that gate is known as a phase gate. Quantum computing is far more powerful, and we can see it even when we have just the smallest possible quantum mechanical system, which is a single qubit. Classically, there are only two logical gates that can be applied to a single bit, which is identity, so bit is left unchanged, and NOT gate, a gate that would change 0 to 1 and 1 into 0. But quantumly, we have infinitely many quantum logic gates that can be applied to a single qubit. So for example, which is a very nice illustration of this principle, in classical computing, we don't have a function that when applied twice would flip the bit, because we only have two gates, identity and NOT. If we apply NOT 2 times, we get to the initial state. There is no classical gate that we can apply to a bit 2 times, and the result would be a NOT gate. But in quantum computing, we have square root of NOT. So this matrix is the square root of naught. If you multiply it twice, we get to the power x. We also have a very interesting gate called ADMR, which creates an equal superposition if applied to state 0 or state 1. So say we measure the qubit, we measure it at a 0. After that, we apply ADMR gate, and we transform our qubit state into equal superposition of states 0 and 1. Again, nothing like this exists in classical computing. What is also interesting about ADMR is that when applied, say, to state 0, here, we get an equal superposition of states 0 and 1. But what happens if you apply ADMR second time? So what would happen if we apply ADMR to the superposition, to the equal superposition of states 0 and 1? One would think that we would still end up with a superposition of states 0 and 1, right? Because we have here 1, here 0. So we have superposition of superposition. But actually, applying ADMR second time would take us back to the initial state 0. We can verify it with simple algebraic operations, but it also shows that ADMR is its own inverse. Applying ADMR twice is the same as applying identity. And it also illustrates the fact how probability amplitudes can interfere. Sometimes they would end up, sometimes they would cancel out each other. So this is an example how quantum gates, these unitary matrices, unitary operators, can perform operations that simply don't exist in classical computing. So before we only spoke about superposition. Now we need to talk about entanglement, because the real power of quantum computing comes from entanglement. When we have a one-qubit system, we have two basis states, 0 and 1. When we have two-qubit system, we have four basis states, 0, 0, 0, 1, 1, 0, 1, 1. When we have three-qubit system, we have 8 basis states, and so on. So generally, the n-qubit system would live in a 2 into n dimensional Hilbert space. It means that in general case, when the system is entangled, and we'll talk about entanglement, we would need 2 into power n probability amplitudes to fully describe the system, which is essentially the amount of information we can encode in the system. So with, say, 100 qubits, we can encode 2 to the power 100 probability amplitudes. So that's how much information this tiny system can hold. So entanglement is almost a synonym to correlation. So when qubits are entangled, it means that they're not independent, they're correlated. And effectively, all these probability amplitudes, we need so many of them because information is not stored in individual qubit states. The information is stored in correlation between qubits. But if system is not entangled, if our qubits are totally independent, we don't actually need 2 into power n probability amplitudes to fully describe the system, right? If qubits are independent, for each qubit, we only need 2 probability amplitudes. So we would need 2 times n probability amplitudes to fully specify our system. It's only when qubits are entangled, they're correlated, that we cannot measure one qubit and leave all other qubits unchanged, that we can have this 2 times n probability amplitudes. And this is essentially the difference between a classical system and quantum mechanical system. Classical system with n bits, it's 2 times n. Quantum system with n bits, it's 2 to the power n. So now is time to talk a little bit about what kind of quantum computers we have at the moment, what is possible. So here we have the whole range of existing quantum hardware produced by Rigetti Computing. There's a quantum hardware manufacturer based in Berkeley, California. Their most recent quantum chip, called Aspen M3, has 80 qubits, and a single qubit gate fidelity is 99.9%. So fidelity means effectively it indicates the error rate. 99.9% is actually quite good. It's not great. We definitely cannot run Shor's algorithm on this hardware, but this fidelity is already high enough to experiment with quantum algorithms that we are going to talk about in a few minutes. And 80 qubits, is it a lot? Well, 2 to power 80 probability amplitudes seems like a lot of information we can encode in the system if you know how to do it. So a system would be initialized in a particular state. For example, all qubits would be initialized in state 0. And then we would run a quantum circuit. We would apply a sequence of quantum logic gates that will transform the memory state, the quantum mechanical state. And we would end up with some probability distribution encoded with the help of 2 to the power 80 probability amplitudes. So potentially, we have a lot of information that can be encoded in the system. A good comparison is always to look at number of particles in observable universe. So as we know, there are 10 to the power 80 hydrogen atoms in observable universe. So 2 to the power 80 is already quite astronomical number, if you wish. So we can do some serious stuff even with existing quantum hardware. So now is time to move to the next item, which is actually quantum machine learning. So we know the power of quantum mechanical systems. We know that the systems can encode a lot of information in probability amplitudes, and we know that we can manipulate on probability amplitudes by applying quantum logic gates, mathematically described as unitary matrices. But we can do more than that. If we have several quantum registers, so a system that consists of, say, n qubits, and the system exists in a particular state, we call it psi, then we can apply a sequence of quantum logic gates, the circuit, and then perform a measurement on all quantum registers. So we would measure all the qubits. What we have here is the parameterized quantum circuit. Parameterized because all these quantum logic gates generally would have what we call adjustable parameters. These are rotation angles, thetas and phis, that we can apply to individual qubits. So some gates would be 1 qubit gates. We would manipulate on a single qubit. Some gates would be multi-qubit gates, where we would simultaneously operate on several qubits. So we would connect them and bundle them. And then we perform measurement in the end. So here we have effectively a set of parameters that uniquely specify how we manipulate on this quantum state, how we change it. And these parameters, they can be trained. And if we can train them, meaning we can find, in some sense, optimal configuration of these parameters, it means that we can build effectively a quantum neural network. So say we have a particular ansatz, particular configuration of quantum logic gates specified on a set of qubits. And we have some classical data, which we say want to classify. for the sake of simplicity, let's assume we have a simple binary classification problem. So we have a data set with a few thousand samples, a few hundred features, and we want to perform binary classification. What would we do? First, we need to encode this classical data into initial quantum state, and after that, we would have our circuit, parameterized quantum circuit, that would try to change, to modify this quantum state and perform measurement, and the measurement should give us the class label. So the training protocol is a hybrid quantum classical protocol where we would first classically specify all the parameters for the quantum circuit, then we run the quantum circuit before measurement. Then again, based on the measurement results, we would calculate some kind of loss function classically, and then again, classically, we would update parameters, and this loop continues as many times as we want or until some criteria is reached. So this is an example of a simple quantum neural network that performs this binary classification. The first part of the circuit is sample encoding. So in this case, we have 8 quantum registers. So we have just 8-qubit quantum system, really tiny quantum mechanical system. And you see that we would start with all qubits initialized as zeros, and then we would apply rotations around various axes. We can first apply rotation around x-axis. Think about Bloch sphere. So first we rotate, starting from 0, we would rotate around x-axis by some angle phi. Then we would perform second rotation around another axis, orthogonal axis, for example, axis y. And these rotation angles effectively encode the classical features, classical variables, say continuous variables or integer variables or binary variables. Because there is always one-to-one correspondence. We can always establish one-to-one correspondence between a continuous variable and a rotation angle on interval 0 pi. So that's how we encode the classical sample into quantum state. After that, once we have prepared the quantum state, we change it, we modify it with the help of a parameterized quantum circuit, where we have a range of parameters, adjustable parameters, and we would try to find their optimal configuration, and some logic gates which are not adjustable. For example, 2-qubit logic gates like this. They're not adjustable, but they help us to create entanglement. So effectively, we would create a very rich, very interesting quantum state. And finally, we perform measurement. Since we want to build a binary classifier, we only need to measure a single qubit, and we would interpret 0 as class 0 and 1 as class 1. If we would have a multi-class classification problem, not binary, but multi-class classification problem, we would have to measure several qubits. And then we would interpret 0, 0 as class 0, 0, 1 as class 1, 1, 0 as class 2, and so on. So the quantum circuit that was just shown on the previous page was applied to a quite well-known data set from UCI machine learning repository called Australian Credit Approval Dataset, so use case from finance. This is a data set that consists of 690 samples. It's a binary classification problem, so credit application can be either accepted or rejected. And it has 14 features. 14 features that describe the financial state of an applicant. We can think about them as some abstract features, some abstract continuous variables. What is interesting is that if you look at this, I go back one page. If you look at this quantum circuit, we see that it's extremely simple. You can't build a neural network or quantum neural network simpler than that. We encode classical data with just simple rotations, and then we have a simple tree structure with final measurement on just single qubit. The simplest possible network. And this very simple neural network, which was trained with a particle swarm optimization algorithm, performs at the same level as all classical benchmarks, which were specifically optimized for this task. So if you look at a simple feed-forward neural network like MLP, if you look at gradient boosting algorithm, if you look at SVM, logistic regression, all these algorithms perform roughly at the same level, and QNN is right there. So this very simple neural network performs at par with optimized classical benchmarks. But what is interesting is that there is a unique feature of a quantum circuit which is very important for machine learning use cases. This feature is extremely strong regularization. It's almost impossible to overfit a quantum neural network. And this page illustrates this point. If you think about quantum circuit, it's essentially just a very large unitary matrix. It's a linear operator. So here we're talking about essentially a linear model. A linear model would generally not have the same expressive power as, say, nonlinear feed-forward neural network, because neural network would have activation units performing nonlinear transformations, right? It has very rich structure, but because here we operate on a system that lives in an extremely high-dimensional Hilbert space, we effectively can perform classification easily. So quantum neural network effectively combines the regularization power of a linear model with the fact that it operates in a very high-dimensional space, not dissimilar to what SVM would do, right? So, for example, if you would have this kernel trick and we would map our samples into a very high-dimensional space, that's exactly what we have here. In contrast, a feed-forward neural network would rely on some kind of regularization, like Tikhonov regularization controlled by some regularization parameter. Here we have example where we took MLP classifier with 2 hidden layers. We put the same number of activation units in the hidden layers as the number of our features. In this case, this data set has 14 features, so we had 14 activation units in every hidden layer. And then we tried different values for the regularization parameter, alpha. And the way to monitor performance of this classical benchmark classical classifier was to look at in-sample and out-of-sample performance, but also we can monitor degree of regularization by calculating the upper bound of the Lipschitz constant. A Lipschitz constant can be thought about as essentially the largest possible degree to which the matrix of neural network weights can stretch the vector. So the input is a vector, and then each layer in the neural network essentially gives us the matrix of weights, and this matrix of weights would try to transform the signal. So we start with some input, then first hidden layer, then second hidden layer would transform this input, and then we would have the outcome. So the degree to which the signal is transformed depends on the magnitude of weights. And when we overfit, very often it is because some weights are very large. So regularization parameter alpha penalizes large weights. So that's how we regularize. We add a penalty term to the loss function, and we penalize very large weights. So when alpha increases, we penalize large weights more and more. So through the training process, we find configuration of neural network weights with weights that get progressively smaller. And correspondingly, we build matrices of weights that would stretch input vector less and less. So we start with alpha, which is very small, that clearly overfits. We get 1 for F1 scorer in sample, but only 0.78 for F1 scorer out of sample. And the Lipschitz constant is very large. And when alpha increases, regularization increases, and the model becomes effectively more and more linear, if you wish. At some point, we find a sweet spot. So there is parameter alpha, which is equal to 10, which is very strong regularization. At this point, in sample and out of sample results are approximately the same. And we can see that Lipschitz constant gets closer to 1. It's 1.3. While for QNN, Lipschitz constant is 1 by construction because it's just a unitary matrix. But what happens if we continue to increase the regularization for this feed-forward neural network? When alpha gets to 40, we can see that in-sample performance suffers, Lipschitz constant becomes less than 1, and small additional increase in the regularization parameter effectively destroys the classifier altogether. So this is what is special about quantum neural network. It's a powerful machine learning model because it operates in extremely highly dimensional space, but also due to the fact that it's just a big unitary matrix, it has a Lipschitz constant equal to 1 and provides very strong regularization without any extra effort on our side. So unlike with classical neural network, we don't need to search for the optimal hyperparameter, which is our regularization parameter. Then we can also build generative models. In the previous example, we measured qubit. The output would be 0 or 1, which would be class 0, class 1. But we can also use parameterized quantum circuit to build a generative model from which we can sample. Again, we would initialize all qubits as zeros. We would encode the quantum state through applying various rotation operators and 2 qubit gates to create entanglement, and then we would perform measurement in the end. So the whole circuit here, up to the last layer, up to the measurement operators, effectively creates a particular quantum state, which encodes a desired probability distribution. And the measurement would produce a bit string, which is a sample from the encoded probability distribution. So this is just a powerful sampler. And this is my last slide, because we are running out of time. So here we have example where this quantum circuit board machine, this generative model, was trained on a financial data set of S&P 500 daily returns. And we can see that the model managed to, it was trained with genetic algorithm. And we see that the optimal configuration of all these model parameters, which we managed to find, effectively helps us to encode the right probability distribution, sampling from which will give us samples which are effectively indistinguishable from the original training data set, as we see from the QQ plot. The upper chart shows quantile plot of data against normal, where we can clearly see that it's a heavy tail distribution. It deviates a lot from normal distribution, and the QQ plot of data set against QCBM generated samples fall almost perfectly on diagonal, which means that we managed to train model properly, and we managed to generate samples which are statistically very close to the original data set. So we can build very powerful sampler of synthetic data with parameterized quantum circuits. So that's everything I wanted to present today. I don't know if we have time for questions. Thank you very much.
Thank you, Oleksiy. So for our second topic for today's event will be about machine learning meets statistical physics, a Web3 perspective. This session will be delivered by Mr. Matteo Manzi. Over to you, please.
Thank you very much. Good afternoon, everyone, and thanks, Gutierrez, for the invitation and everyone for the organization. So I tried to encode in the title 3 points that are characterizing the work and the research we've been doing in CrunchDAO. I'm happy about the first presentation because you warmed up many concepts that I will try to build on, particularly with this statistical physics meets machine learning in many ways. A statistical physics approach to quantitative finance is similar to a quantum approach, I would say, in the sense that we use a Hilbert space formalization and we reason in high-dimensional space to avoid overfitting, among other things. But yeah, so in CrunchDAO, we are performing ensemble learning. So we use machine learning in financial data to predict the stock market, basically, in some sense. So the idea is that similarly to the previous presentation, we have a set of observables, which is a term associated both with quantum mechanics, but also statistical physics, that we are basically tracking to have a finite dimensional representation of our system, which is living in Hilbert space. We have to do something about this, among other things, because these observables are non-stationary, but also because they're fat-tailed, so not Gaussian distributed, and we want to build inference models on this representation of the system. So yeah, I would say mainly the discussion will be about this feature engineering step and all the pipeline. I will try to underline some interesting implications of performing ensemble learning in the context of quantitative finance, mainly the implications for portfolio optimization, and also touching on the ergodic hypothesis in financial data, meaning that the meaning of stationarity for us is a cross-sectional one. So we are not tracking individual trajectories in time of these observables, but we are making stationary in a cross-sectional sense. But this requires the ergodic hypothesis to hold. So a bit of a framework, which is traditional econometrics. We have a linear system, a linear representation of the return of an asset, and we have a set of factors. So this is a sparse basis, because the dimensionality of F, the dimensionality of F is much smaller than the dimensionality of a universe, so the number of assets we're tracking. So we have this, let's say this is a given in our framework in this presentation. And so we have a linear representation of the return that's approximating in some sense, that's best fitting in some sense the return given an error. So yeah, nothing new, let's say, just a warm-up. We are interested in building a portfolio which is neutral to some subset of factors which are given by the literature in econometrics. And to do this, we want to impose zero exposure. So in this sense, we want to make the portfolio orthogonal to the factor exposure at that moment in time. And for this implies that then the expected return of the portfolio is all represented inside the specific return, so a non-linearly modeled return. And so, yeah, in CrunchDAO, we're using machine learning to do this, to capture these non-linearities. And yeah, I would say this is an interesting paper in this context. But yeah, these three works all build on traditional econometrics using the concepts of machine learning. So yeah, our system is basically evolving in time, and it's represented by a set of observables which are associated to different, talking in statistical physics sense, different realizations of the same stochastic process. More practically, we're looking at a set of stocks, and then we have a number of observables. So we have this matrix, X matrix, which is our feature, our representation of the system. And we want to build some model that can, in a supervised learning framework, help us build a model that's predicting some target. Let me get some water. So you see, these are some examples of features. I think in this work I'm listing 7, but they're in general non-Gaussian, and we will treat this in the following slides. And these are other features I'm considering these slides. So the starting point for us is that we want to have a portfolio which is orthogonal to factors, and to inform the representation of the system with this hypothesis, let's say, with this design choice, we want to make the features orthogonal to this factor basis. So this is a finite dimensional basis that we can put together with a norm, so a distance, which in our case is a correlation. Pearson correlation in particular, implying dot product orthogonalization because of the standardization of the exposure vector. And we want to do this because if we build nonlinear models trying to predict some target y, and the model is f, using Taylor, we can see that there's going to be a linear component for this model. So this is a trivial Taylor expansion. And since we want the correlation between, basically, we want this to be 0, we want this because this implies that we're going to get a return that's going to be fully nonlinear representation of the factor exposure. So here is some norm for the exposure in time of our dataset to the features, to the factors, sorry. And this is the exposure, again, in some norm sense of the set of features after orthogonalization. One important point is that factors in general do not form an orthogonal basis. So we cannot hope to orthogonalize against the first one, then the second, and converge to some space which is orthogonal to all of them. But we have to approximate because they're not orthogonal to each other. And so in this work, we went forward with a linear square regression. So we orthogonalize in a least square sense. And we use this equation to solve the least square problem. And we obtain new features. And this is how they look like. They're still highly non-Gaussian. And so at this point, we do something like support vector machine in the sense that we define an implicit kernel, an implicit metric that allows us to go in a space in which the distributions are Gaussian. Yeah, and in particular, we use this work, an interesting work in which we build a map which is invariant in time that allows us to go from some highly non-Gaussian space to a Gaussian space. We build inference models in this space, and then we go back to the original physical space, let's say, in which we want to do prediction. You can think of this as an analogy of when we have volatility clustering and we want to, in some sense, standardize the risk taking it into account, building a portfolio, and then going back to physical space, building from the desired level of risk of each asset to the size in the portfolio of each stock. So this is a graph of what I just said. We start from Y, observed heavy tails, which is what we have. We build a map that allows us to go in a Gaussian space. And this is basically doing the kernel trick. We are not building an explicit analytical kernel, but we are going in Hilbert space. And then we can do things in this place in which things are Gaussian and go back to physical space. So we do this. These are the input features and the Gaussian associated with the same standard deviation. At the end of the procedure, we get something like this. So yeah, it's interesting to see that the correlation between the output features and the input one is more than 98%. So good news. Also because of the low level of non-stationarity at this point, because we orthogonalized against a set of factors which are stationary in a cross-sectional sense, we can build global transformations that allow us to perform orthogonalization among features. So we are now in this space which is orthogonal to all the factors. And in this space, we want to extract the maximum amount of information from the set of observables we have. We did Gaussianization to go in a space which is well suited for performing orthogonalization. And so we can do standardization followed by principal component analysis. Sorry. So yeah, we can perform stationarization followed by principal component analysis, then stationarization again. I'll give you all the steps later, which allows us to normalize in some sense the different features that have a different physical meaning. So this is all together. We perform orthogonalization, then Gaussianization, standardization, principal component analysis, a linear combination, and then standardization again. All the steps we do after Gaussianization are linear, so we are always moving inside the space orthogonal to the factor basis. These are the features we get at the end. And this is the covariance matrix, so good news. We are orthogonal in the space spanned by the orthogonalized observables. And because we want to have this as a representation of the system, we are not really interested in going back to physical space. Let's say, having built this nonlinear map of the physical space, we are only interested in having a representation which is highly correlated with the physical observation. So we can use this to build inference models. Because in CrunchDAO we are sharing the data, we have to anonymize them. And to do this, we quantize the process. And if you think of this as a process in time, let's say this is a Gaussian process. And so you can represent it as let's say a time series. But here you have stock number, particle in a statistical physics sense, and value. And this is evolving in time. And quantizing it with the Lloyd max quantization, we are able to get something like a digital Gaussian process. So you have, I think in this plot, 7 quantization steps. And this scheme optimizes for the quantization in a least square sense, which kind of makes sense because we have a Gaussian process to start with. So optimizing for unexplained variance is the most natural choice. And we obtain features like this, which can be thought of as basically a k-mean clustering, so a clustering algorithm in which we're interested in finding the position of the centroid, so the bins that are gonna represent the input value, such that the information is not lost. So about the targets, this is the representation of the system. We want to build this on these inference models, and we want to predict something. So we have some target that represents some kind of risk-adjusted expected return for the future. And we see that these are highly non-Gaussian as well. And so let's say if we were to get exposed to this kind of return, we would not build a portfolio which is alpha score-like, so cumulative Gaussian, but something much more extreme. You see that a lot of return is captured by the tails of the distribution. So in order to, again, inform the data and let the machine learning models implicitly learn that it's more important to get right the worst and the best stocks in the universe, we quantize following the distribution, which is non-zero kurtosis. And you see this in this distribution, which is highly non-Gaussian. And in this way, using a linear scorer to train our models, we are still in a good place because the discretization done in this way informs the model of the right weight to give to different stocks. Of course, if we didn't need to do the anonymization, we could use this metric as a weight for a nonlinear fitness function to optimize our models. This is it. I think I was pretty quick. Yes, super quick. But yeah, let's open up a discussion then, I guess. So yeah, thank you.
Thank you, Matthew.
Oh, just a simple one. Can you re-explain or repeat why you need to neutralize the predictions?
Yes.
Thank you.
So this part here, you need so we want to build a portfolio that's neutral to some factors. So we want a portfolio whose return is orthogonal to factors. So we want to maximize the exposure to the component of return which is orthogonal to factors. At the same time, we want to maximize the exposure we have to the nonlinear, to the idiosyncratic return. And so we want to have this. I mean, we want to have a high correlation between the prediction and the target, and a low correlation between the prediction and the factors. And since we want a high correlation between the portfolio weights and the predictions, there's an implication that we want the features that we are building models on to be orthogonal to factors. We could be missing something in the sense that there could be models built on the original features, which are nonlinear models, which are orthogonalized after that, which encapsulate more about the predictive power of the features. But this is the first solution we wanted to explore. So.
Oh, thanks for the presentation. I have a question that's probably on everyone's mind here, and that is, if any of this works, why share it? Why have a DAO for it? Why not just trade?
Yeah, good question. Yeah, so this is just research, so it's not part of the implementation in the DAO yet. We believe two things. One is that with sharing it, we gain more than what we lose in terms of competitive advantage, because we can attract really good people that, because of the infrastructure of DAO, I didn't talk about it, but the tokenomics allows us to work in a decentralized way, and so by sharing we attract. So I would say we lose, but we win more than what we lose. And the second thing is that by doing ensemble learning in a DAO fashion allows us both to perform ensemble averaging and so to, in some way, reduce overfitting, allows us also to have a metric of the distributions of predictions, which we can use as an input for the portfolio optimization step. So we have much more to gain than what we lose, which, I mean, I think what we lose is clear. We lose competitive advantage by doing part of this, but we believe we win more than what we lose. We gain more than what we lose. Yeah.
You are really losing if you are orthogonalizing the. All right. So I'm not totally convinced by the step of orthogonalizing the features, because what you want if you sell a hedge fund, which is not necessarily what you want to sell, but if you sell that, you want the predictions that are orthogonal to factors that your clients already have exposure on. But it doesn't mean that the features themselves have to be orthogonal. So that's a step that I think it's not necessary. Or maybe there is a justification.
Yeah, no, for us, the justification is in the fact that we wanted to, because we're doing it in a tournament structure, we wanted people to be able to build models and score the model before the neutralization step. So an easy solution would have been to build models on these non-neutralized features, neutralize the prediction, and score based on the neutralized.
So in short, it's a shortcut to make sure that the contestants are not loading on factors.
Exactly.
All right.
But we're losing something, maybe too much.
No, very clear. Thanks.
Thank you.
So if no more questions, let's thank the speaker again.
Thank you.
And we will have our last speaker of the date, but not least, Professor Jorge Zubelli, Chairman of KU University.
I will use the hands off. Oh. May I? Okay, well, thank you very much for being here. Let me thank Peter Ward. Let me thank Rhoda for putting this together, Gauthier. It's good to see some friends, and I hope to build more friends with this presentation, or despite this presentation, perhaps. So I'm going to talk about project evaluation. I understand the pointer doesn't work. I will try to point as I go along. I'm going to move a lot. I believe in statistical mechanics and quantum mechanics. I cannot simulate quantum effects here, but I will try to move as much as possible so that I have increase in the entropy and increase in the thermal instability. So, by the way, talking about statistical mechanics, I hope at a certain point I'll mention that there's a lot of connection between what I'm doing in statistical mechanics. I do believe on this intrinsic unit of mathematics, physics, and science in general, and finance these days. So, just to give you an outline of my talk, I'll give you some background. I'm going to talk about the so-called hedged Monte Carlo algorithm, and it's good that we had statistical mechanics before, because HMC was actually originally used in finance by Jean-Philippe Bouchot, whom I'm sure that my French colleagues know very much about him. He is a physicist that moved into finance, and he actually worked on statistical physics. So the algorithm that I'm going to talk about is inspired on his work. I'm going to discuss some data-driven examples, And then I'll go again to the French school, to some work that I did together with my good friend Emmanuel Cobé at the Polytechnique, which is connected to everything else that I was talking about. And finally, I move to Abu Dhabi and talk about some work that we have been doing at Khalifa University with some of colleagues. I'd like to acknowledge the presence of Professor Giorgio Consigli here. Some of my colleagues cannot be here because we actually have a seminar that coincides with the meetings here. We are going to, don't worry, we're going to move our seminars. So what am I going to be talking about? I'm going to be basically talking about, and sorry for my voice, it's part of the uncertainties of life. So I'm going to talk about how to evaluate projects and their optionalities under uncertainty in a consistent way with market fluctuations. And by consistent, I mean in a way that not only the projects are trying to give you the best value, but you have the option or the possibility, if you wish, of investing some of your money in the stock market or in the futures or commodities or any instruments that you like, okay? So what we are interested on is assigning monetary value to strategic decisions. For example, create a startup perhaps of quantum finance, invest in an oil field. I'm sure that this is a problem that is interesting for many of you, perhaps even most of you here, investing real estate development, finance a research and development project, like, for example, the one on the quantum computing at Barclays that was discussed today. Perhaps temporarily suspend operations under adverse conditions, like shutting down an industry. So those decisions, they do have financial implications, and they should have, of course, value. So how do you estimate such values? That's the question that we're discussing here. From the perspective of financial mathematics, from the perspective of someone working on finance, what are the issues that we are talking about? Well, we are talking about complex claims, barrier clauses, I hope I don't destroy this, exotic characters, exotic in the sense of exotic options, presence of cash flows and decision trees, optimal exercise times. And the interesting thing here is a mixture of historical and risk neutral measures. I don't know how many people are familiar with this, but in very simple words, when you are investing, let's say, in the stock market, and you have some kind of ideal equilibrium conditions, again, alluding to to statistical mechanics. If you have all those hypotheses, then you have the so-called risk-neutral measure, risk-neutral valuation of stocks, portfolios, and options. But on the other hand, we have real things going on. You have historical prices, you have prices that are not hedgeable. You therefore have to mix the two. So this is actually a very interesting problem, and there are different ways of dealing with that. People in finance and econometrics and economics have been worrying about this. So what are the so-called real options? The name comes from the work of Stuart Myers, and it was coined by him. It refers to options that are not necessarily financial, they are world options, and perhaps an allusion of real estate. For example, are you going to start a real estate development? Are you going to build a new building here at Marais Island, for example? Well, you have to talk to ADGM about that, and ADGM might be interested in that question. I hope so. So what we want to do is we want to capture non-passive managerial values of projects. What is non-passive is the possibility of deciding later on some different strategies, what to do, and so on and so forth. The original idea here has a very clear connection with math finance. And try to remember, probably from a very elementary course in finance, what is a call option. So what's a call option? Basically, it's an option that after some time, you may have the right, but not the obligation of buying something for a given price. Now, the payoff of that option is going to be positive if the value of this thing is bigger than the investing or the strike price that you have, okay? Well, project is something like that in many situations. You have a cash flow that you can accumulate as a result of investing your money. So at a certain time in the future, you decide to invest a certain capital, and as a result, you get value out of that. Now, what happens, okay, there's a feedback here, that's very good. It's meaning that the system is amplifying. So what happens is that the moment in the future you want to invest is not necessarily a certain time, but it might be an uncertain time, something that you don't know, what we call in statistics and probability a stopping time, a random time, okay? And this makes the problem much more interesting. It alludes immediately to American options, the options that you can exercise at any moment, let's say from now to a certain expiration date. So this is where I'm getting at. The very early applications of the theory of real options were just mimicking European options, vanilla options very early, but then people were talking about American options, Jamaican options in between, and so on and so forth. A bit of background as far as credits. Black-Scholes in '73, they became very famous because, and they got, Scholes got the Nobel Prize for that, pricing options and also corporate liabilities. Usually people forget about the corporate liabilities part, only the options they mention, but corporate liabilities are again this type of real options that I'm talking about. So if you look at the very last sections of the paper, it's about that. So they were already discussing this in that paper, and Merton later on with jumps and so on and so forth. So this is a very interesting subject, and these papers are still source of so many interesting ideas. Now Myers, I mentioned, is the one who came up with this idea. Octavio Torinho was a student in Berkeley, and he did a very interesting thesis, which also dates from that time, of the option valuation of natural reserves, natural resources. And again, this alludes very closer to our hearts here. So how to assign monetary value to, let's say, the possibility of starting the development of an oil field or closing down an oil field and so on and so forth. McDonald Siegel, Myers and Knight. So the list of, I mean, this became a very, very important area in corporate finance. There are even courses about that. But I don't want to dwell, let's say, on the classical part. I want to go into, let's say, the crux of the matter from the mathematical point of view, which brings in really practical problems. By the way, I should mention that the way I got involved into this was by looking at these real options for the Brazilian oil company Petrobras. Brás is Brazil, Petro of Brazil. So we had a number of projects with them while I was in Rio, and they were very interested in this, as well as a number of other companies, oil companies throughout the world. And there's a list of them. So So let me try to give you the main idea, the main crux of the matter. What are the ingredients here? Just for those of you who have never seen this, I'm sorry to be pedestrian, but I think it's better to start slow and accelerate than to start, then do the opposite. So we have a value V, which depends on time. So this is the value of, let's say, your total value of your company, or the value of part of your company, okay? Values as companies, as you know, are certainly correlated tremendously with stock prices, and are correlated tremendously with commodities, for example, in the situation of oil companies, or in the case of pharmaceutical companies are related to stock value of companies. So we are going to invest. We are going to invest with a certain value I. By the way, that value I usually is something fixed. That's something that you fix ahead of time. But sometimes it might be even a random variable. And actually, I did some work together with people at Toronto on that, but we are, for the time being, concentrated on that case. I is fixed. And as I mentioned before, it looks like the payoff of a call option. You have to discount, you have to take the expected value, and you take the soup of all possible exercise times between today and your expiration date. So this is one way that one can look at the value of the project. Note that here, so far, don't look at this, I have no model implied. I'm just stating something that makes sense. What is the dynamics of V is another story. What drives V, what factors you have to put in the decision, in the simulation of V, how do you compute this expected value is another story, and so on and so forth. Okay? Well, example of a model for V, classical stochastic differential equation. If you don't like stochastic differential equations, no problem. Intuitively, this increment of V is proportional to V times dt. It's like growth rate by a rate R minus delta, plus some random part, which is the famous or the infamous volatility of your stock or your investment. This is just one model. Now, the issue is, I was talking about value of a company. Why can I write that? This is a totally natural question. In fact, in general, I cannot. In general, my value of the company is going to be a very nonlinear value function of the stock. It might be even a non-causal thing or a non-Markovian thing. Okay, so there are all kinds of complications. However, we have finite amount of time, life short. You have to simplify other models, otherwise you don't do anything. So just to give you a dictionary between the financial world and the real option world, one side you have financial options, the other side you have real options. One side you have the underlying price, on the other side you have the project's present value. You have the variance of the stock. On the other side, you have the variance of the return. The exercise price is related to the development cost. For example, if you're starting a real estate thing, you have to start with some money. Expiration date is the time limit for the investment. Risk-free is the risk-free rate for the investment. Rate, dividend, is the risk-adjusted return. Okay, so if you wish, I can go through that more in detail later, but in any case, what are the usual assumptions? Infinite time horizon. You can usually, in the simplifying world of real options, oftentimes people talk about an infinite time horizon, that things that you can do when the time is not infinite. Perfect correlation between your value of the company and some kind of spanning asset. Let me give you a concrete example. If your revenue from the company is basically coming from oil and oil prices, the value of the company is going to be extremely correlated with the oil price. This alludes to the original application of these people studying copper mines, and they were asking the question, you know, how much should, or when should I invest in a copper mine? And the copper, the price of the companies, the price of the mines were highly correlated with the price of the copper in the international markets. So this is not such a bad assumption. However, it's not necessarily true. And there are all kinds of things. For example, it assumes that there is no competition, that, you know, you get the thing out of the floor of the earth, and then you sell it, and that's it. But perhaps another company has a strategic competition, a strategic advantage over you by putting your refinery in a very strategic place. You are able to beat the prices. Okay, so there are things that are along the sides. Now, from the, let's say, economical and financial point of view, there is a very serious critique about the use of real options. There are several critiques. I mean, this is a model, these are models, and every model is imperfect. Some are good. It's not my quote, it's a quote of the wise. Schachmeier from Vienna and Hubalek, they actually have a very interesting paper about the so-called no arbitrage arguments for real options. And this motivated, this kind of critique motivated type of work that we are doing, besides the fact that we had to give answers to our project sponsors. So in the case of these project sponsors that I'm talking about, what was the way they operated? So they want to do planning, they want to decide, they want to take strategic decisions. And this is something that doesn't happen only for Petrobras. I'm sure many companies, I don't know if anyone is using it here, but I'm sure that there are lots of companies, they have some kind of oracle to estimate their cash flow, some kind of very complicated scheme of everything that happens in the company. So for example, a truck goes from one place to another with a load of gasoline, how much it's going to cost, how much it's going to make, how much it's going to receive. And this kind of thing is incorporated in very big programs, very big software that can generate, given the traded and the non-traded assets that the company has, the cash flow associated to that. Usually it's over a month, okay? Over a year sometimes, over a semester, but it's they do this a lot. Now, what happens if then they build a new refinery or they shut down some oil gas pipeline? Or what happens? Well, they can decide, they can find out what impact it's going to have in the cash flows. So you see, from a, let's say, computational science point of view, you have this machine that takes data and somehow crunches the data and produces your expected your cash flows. And of course, these are random variables. So these are going to be random variables, highly nonlinear. So the question now is, what can you do with this? Okay, and how can you evaluate things? Note that nothing here is analytic, everything is analyzable. And you don't have explicit expression for anything. So you have to really rely on real data. Now, as I said, the cash flows of the project values are highly dependent in commodity price. I'm now talking about energy industry. There is some financial hedging. For example, many of these companies, they have a trading desk where they can buy Brent and sell WTI, or I'm making up, but they can do this kind of thing. And they can use that in order to do some protection. Often the profit in the cash flows come from spreads between prices, the fact that they are producing, for example, gasoline at a cheaper price than the market, and they make a profit by selling at the market price, for example. Usually for evaluating projects, this oracle is run with and without the project you're trying to evaluate. And the evaluations of the cash flows, they take a lot of time. So you want to do it in the most efficient way. That brings in a lot of machine learning questions. For example, what are the best basics? What are the best approximations that you can have when you go back here and you compute C, but then you have to vary C a little bit. How do you do it, okay? There are windows of opportunity, possibility of expansion, complex optionalities. So all these things are natural questions. By the way, if you want to escape and want to read about what I'm talking about, this is a paper we published a few years ago, 2015. Time flies. We're exactly working and discussing these issues. There has been, of course, some further work, and I'm going to talk about that later. Okay, so what are the challenges? Historical measure. We are working with historical simulations usually, or not working with risk-free or risk-neutral simulations. You have sometimes to incorporate managerial views. You do want to incorporate, for example, the expectation that some events are much more likely than others. So you might not only work with historical for the noise, but you also want to work with trends. You want to talk to your boss or to a board, and the board usually sets up some expectations, for example, on regulation. These guys are wise people. They usually have a lot of insight, and they want to put some bias on some parts of your phase space. Marketing completeness, that has to do with the paper by Shahmaya that I was talking about. Unhedgeable risks, especially in commodities. You might have an earthquake, you might have, God forbid, you might have, you might think of what bad things could happen, or you don't want to think about that, but you have things that you cannot hedge. As I said, we have multiple assets, multiple markets sometimes, okay? So there are different approaches that try to address some of these features. Here they are. I'm not going to go into detail on them unless someone asks me. But what is our point of view, which is this risk minimization approach? What we mean by risk? Well, there are many different ways of evaluating risk. Traditional way of evaluating risk is by looking at the variance, but you can look at one-sided utility functions. You can look at utility functions in general. So you can incorporate different techniques here. But the point is, we take this approach, we can make it data-driven, and we do make it data-driven in the sense of using directly the data that is provided from the market and not fiddling, well, not, let's say, trying to model and the data necessarily. It can be integrated with artificial intelligence and machine learning techniques, and we can take advantage of deep learning, neural networks, and kernel-based methods. So what's the crux of the idea that we implemented in our first paper that I mentioned? This actually is an idea that Jean-Philippe Bouchot, Potters, and Sestovic implemented for valuation of real options. I'll try to give you an idea because it's such a beautiful idea. So V is the price of the option or derivative that you're trying to evaluate. Phi is a portfolio, which is in general factors, how many units of stock you have from IBM, how many units of stock you have from, let's say, ADNOC perhaps, and so on and so forth. Okay, X is the price of these traded assets. Phi.x is the inner product and gives you the total portfolio. Okay, that's the usual thing. So when I look at phi times dot x, I'm actually looking at the value of the portfolio at time t. And that is going to be, hopefully, some kind of tracking or replicating portfolio for my price of the option. Okay, so that difference, when I go one step ahead, is going to become, and then you do the trick of coming from the left, phi times x t plus delta t, and sorry, you look at this value at t plus delta t, you look at the difference, but you bring to present value by some interest rate R, which is usually the risk-free, but it might be other things that you adjust to that. And now, when you bring, you can compare what happened at time t with what happened to time t plus delta t. Does that make sense to everyone? Please stop me here. If you, I'm willing even to take questions now, because otherwise, you know, things, okay, good. Now, once you look at that, you take the square of that. That alludes to what? To looking at the variance. Okay, and you take this bracket here. This is my inheritance from the physics world. This is the expected value of this random variable. Okay, so now you take this expected value, and that's a way of judging or computing your risk. Now, do I need to use square here? No. You want some function that's increasing. You might put some kind of utility function if you wish, but you do want to take some average, because after all, the world is not just yes or no, as we learned in the first talk. You have to put probabilities, and by looking at those probabilities of the different events, you can minimize the risk. Now, how do Potters, Bouchot, and Sestovic approach the problem? They solve for phi and they solve for v, given v of t plus delta t. And you do it backwards. I'm talking, if you know the words Hamilton, Jacob, Bellman, this is an old idea. You solve the problem backwards. You know the value, final value. You go one step further back, sorry, one step back, and you compute the value, one step back, and you keep doing that. Okay, that's a classical way of solving recursively for pricing. Okay, well, you do that. Turns out that if you simulate your process in the historical, not in the risk neutral, you get exactly the same prices of options that you get with the risk neutral world. Why do you get that? Because you're hedging. Okay. Now, this gives us an algorithm. Very briefly, I'm not going to dwell too much. You start with the final value that you assess somehow for the different scenarios. You define and initialize your payoff in the last step, and you solve it backwards by defining, with respect to a certain basis, your value and your portfolio, and then you minimize both in the coefficients. By the way, if you like the kernel trick, this is a good place to use your kernel trick, okay? And you define then at each step backwards the decision, am I going to exercise or am I not going to exercise? Okay, and that's the way you compute usually an American option. I'm giving you the, let's say, the algorithm for an American option. This is something that's extremely powerful. And what can we do with real options for that? Well, we can change a little bit this argmin part. We can do this with other functions. We can actually do a lot in this part because it's a question of optimization. You can regularize with some a priori views. So the possibilities here are very, very broad. Example, I don't know how much time I have. Do I have 5 more minutes? Well, there was a shift. Okay, I promised 10 minutes, okay? All that's separating you from our socializing is my talk, so I'll promise to be brief. So first practical example, energy company considers the optionality of starting a new project, let's say that would last for 11 years. This company has 12 different underlying, gasoline, kerosene, gas, and so on and so forth. The option is exercisable only in a window of 5 years. The company has a trading desk that could, for example, trade different commodities there, buy and sell futures, and the optionality was evaluated using different hedging assets. If you don't do, by the way, any hedging, what happens is basically you are doing everything without hedging, that's okay, and you're basically optimizing with respect to some, forget about the financial market. But still, the financial market is playing a fundamental role, and the hope is that by having a trade desk, you decrease your risk. The more instruments you have at your hand, the better it is for decreasing risk. So the results that I'm going to show are actually with one hedging variable because it's easier to show. And in this case, we use the Brent price. We consider only 2,000 PATs. Why did we do that? Because the evaluation process of the cash flows is extremely lengthy, even in very fast computers. So you want to decrease the number of PATs. Well, then what I'm showing here is the value at a certain future time of the real option. You see that the real option has a positive value. And in this case, the intrinsic value of the investment, in other words, the value V minus the investment cost. Quick question to make sure you are awake now. In this case, at this time, is it worth investing or not? Okay, all right. You see the option has a larger value than the intrinsic value, so it's better to stay with the option and not invest. The moment this crosses, and this happens in future situations, then for certain values of the Brent, it's worth investing, for others, it's not. And that's the way you do this kind of decision, okay? It's extremely powerful. Another example, and this, I'm changing gears here because I'm doing things in this situation where you have, instead of looking, let's say, the quadratic world of expected values, I'm looking at percentiles. So here is the project cash flow distribution for different years between 2014 and 2020. Okay, we published this paper in 2015, so it was natural to, well, actually, we were doing the simulation in 2014, so that's why we start in the past. And different cash flows for different years. We're doing yearly because of accounting procedures. 90% percentile, 5% below, 5% above. This is a distribution. Does it make sense? And this is the mean. You can also draw the median if you wish, the 50%. So these are the cash flows. They have to be brought to present value and added. And if you do that, then this is the project option value distribution, okay? For the notes that it's decreasing because the contributions from the future are not coming in. Sorry, the contributions from the past are not coming in, and the contributions for the future are not so big. So this could happen. It could also increase, doesn't matter. It doesn't, I mean, depends on the case. Okay, now with that, you can question or ask the question, what's the distribution of values. Here is the mean value for V, the minimum and the maximum in these 5% and 95% quantiles. And this is the minimum. We compute this with actually, I mean, you just don't look at it, you have to compute. You compute this optimal minimum initial value for exercise. And so if the value of your parameters are such that you get above, then you exercise. If not, you keep the optionality. Okay, so this allows you to do a lot. Now I'm going to skip the third example. It's an example that is in the paper, but I want to now kind of do a partial conclusion. Perhaps it's my almost final conclusion. Still have 4 minutes. I'm going to exercise the option of going up to 5. We implemented this in an approach that incorporates the managerial views. You can twist, you can reassign values in the phase space. It allows to bypass the problem of using risk-neutral simulations. We can take into account also competition games, and we can make this process very efficient. The implementation is really rather straightforward. The interpretation is what's important here. We also did deferment options, expansion options, so you have an option over an option. And the methodology is model-free in the sense that in principle, we don't have a stochastic differential equation in the background, okay? Now, this led to a number of questions. One of my PhD students actually did part of his thesis on this. Questions such as, suppose that in this scarce data situation, you have ways of predicting what type of stochastic process behind the model is driving everything, perhaps some factors, perhaps some different technologies. So in this case, with Emmanuel Gobet from the Polytechnique, we actually published a paper where using, for example, assumption model, we don't do the parametric calibration, we just use the raw data and we resample the space. And we do this in what we call a generalized framework for solving dynamic programming problems. If you know what I'm talking about, it's basically you start with some expected value, final condition, sorry, with some payoff at the end, and you do successive estimations. This is related to solving some partial differential equations, and this is related to this very, very interesting field of backward stochastic differential equations. It's a way of bypassing, let's say, the inverse problem solution. And so we did this. I'm not going to talk about this today. This perhaps could be another talk. I will basically skip all this part of the talk, just draw a picture. Perhaps you remember when I talk again. The idea is with some models, for example, linear Brownian or arithmetic Brownian motion, geometric Brownian motion, Orsten-Uhlenbeck, and so on and so forth, you can, by using samples from some parts of the space, reconstruct the whole thing. And by using that, we actually prove theorems on how to solve this problem, and we have estimates, okay? So I'd like to finish, and I see some colleagues of mine arriving here. I'd like to make a few comments. We have, I'd like to acknowledge Denis Dutik and Oleksiy Kondratyev, who are here. Oleksiy has been working on optimal stopping problems, real options, energy finance, green energy. Today I was listening to the news. There's a big movement about green energy. So you want to learn about that, talk to Yerken. Giorgio Consiglia already mentioned. Emilio Porco is working on kernel methods in machine learning. Dennis Dutek is an expert on differential equations, numerical methods. And so if you have interesting problems, please bring to us. And with that, I finish for today. Thank you very much. Yes. Oh,
All right.
Sorry. I mean, the chair should decide what I should do.
All right. Question in the back.
Thank you, Professor, for the wonderful presentation.
Thank you.
You spoke about capturing some of the non-passive managerial values, metrics in your thing. What role it plays in your algorithm? What you have to explain, probably, if you can spend some time, throw some light.
Well, the non-passive is, the usual, let's say, old way of running a business is you put the money there, you let it grow according to, the company profit every month and so on and so forth. You might take some decisions, but in many situations, when you're really running a big corporation, you want to see, for example, what impact your products would make into the market. Now, there are different ways of doing that. You can analyze it as a game, theoretical, but ultimately you are interested in seeing the spread of doing a decision as vis-a-vis not taking that decision, doing that improvement or not doing it. And in this sense, you are doing things on a non-passive way. That's what I meant by it. Okay, but I mean, it's open to your imagination because there are so many different possibilities here. Yes. Please don't ask me about my advantage competitiveness because I'm an academician. My competitiveness is published papers and age index.
Okay, sure. You went over some of the risk, the papers on risk, and you said, here are all the alternatives and things like that. Which of those papers do you think take account, for like kind of real life uncertainty in business environments, like you talked about oil fields and things like that? Which would you, if you had to kind of pick one for recommended reading, which one would you recommend?
Okay. Given that's not my paper, let me suggest I would, but again, it's a biased response because the author is a friend of mine, a very good friend of mine and collaborator, but I would recommend a paper by Jai Mungal, and it's not quoted here. Thank you. I go to the end. It's probably quoted in the end. My God, didn't I quote him? Okay. Yeah, the name is Sebastian Jai Mungal. Some of you, I'm sure, know. And together with collaborators, I would pick, he's a professor at Toronto University. So I would take his paper because it has a very good summary of what's been done. It's quoted in our paper for sure. Okay, and the other paper from the, let's say, if you are interested in real options, you must certainly look at this work of Trigeorgis and Mason. Okay, so it's hard to select only one, but I would look at the paper by Jai Mungal, which unfortunately I didn't quote here, and but it's quoted in our paper, and Trigeorgis and Mason. Okay, but that's a very good question. I mean, where do you start? Where do you get started?
Good afternoon, Professor.
Okay.
Question
Yes,
here.
please.
Fun question. How do you decide the discount rate? Do you want it stochastic? Do you want it fixed? throughout the project? Do you change it?
The discount rate. This is one of the trickiest things in this area. Now, in the case, what you have to do is look at what the discount rate, means in your application. So I don't want to answer that offhand for the following reason, because when you look at the value specifically, if you go back here in this, and I think you are referring to this discount rate that I put here, right? This, in our methodology, could be stochastic, it could be varying with time, it could be, how do you call it? It could be even event dependent. So the decision in the terms of the algorithm, I don't need to worry about it. In terms of real life, you have to discuss with the manager. And what does it mean to take money, delta t units of time ahead, back to here so that you make this comparison? So ultimately, is going to be the answer that your accounting or your board gives to you when you ask them, $1,000 or $1 million in 1 month, how much is it worth today inside our corporation? Keep in mind, some corporations have banks working for them, and so this rate might be almost nil. For other corporations, it might be very risky. They might have to issue bonds, and so that discount rate varies. So by doing this approach, we avoid all this discussion of what discount rate you're going to do. Of course, you pay the price that you have to run the simulations, yet bypass that problem.
Does it, if you screw it up, does it matter? If you take a bad...
Well, a good question. If you are... Normally, what you do when you do this type of simulation is you do a sensitivity analysis, okay? And the answer to your question, is it going to matter or is it not going to matter? It's a question of computing the sensitivity of your pricing mechanism with respect to your interest rate. In financial terms, it's the derivative with respect to rho, with respect to R, which is called the rho in financial options. Okay, so the answer to your question is depends on the rho, on the Greek rho. Okay, it might make a big difference. It might make no difference at all.
And this concludes another episode of the meetups. So we'll be still around for maybe 30 minutes, 1 hour in the next room where there is, I guess, some catering. So please, if you have questions for today's speaker, Professor Zubeli or Oleksiy or Matteo, go straight to them and they will be happy, I'm sure, to take all the questions. Just one last word before concluding. We are always looking for interesting speakers. So if you are working in the field of machine learning with a bit of applications to finance, please come forward, do a proposal for a talk, and I'm sure we'll manage to organize more meetups thanks to ADGM and ADGM Academy. And yes, so when we have a lineup of interesting speakers, we'll gather again for this kind of event. Thanks again for coming, and I hope you enjoyed the networking events.
Thank you, Gauthier, and thank you for all of our speakers and attendees. I just want to highlight one final note for our virtual attendees to send us their questions through the email that we shared at the beginning of the session, which is research@adgm.com. In case you have any questions in the future, please feel free to contact us anytime, and we will ensure that we receive all of the questions and share them with the relevant speakers. Once again, thank you so much for your attendance, and please join us for some refreshments.